theorem again. And you should have it on your notes, but there we go. Summation as j goes from 0 to n of n choose j, a to the power of, and then b to the power of. Which one of these was just j for an exponent? B is just the power of j. The first one is the power of n minus j. And in fact, let's actually write that out for this problem. Okay? So j is going to go from 0 to what in this case? 4. N is 4. And then it goes it goes n choose j, so 4 choose j. Listen, n is fixed for the problem, n is 4. J is going to vary from term to term. J is going to go from 0 to 4, which, by the way, means how many terms will there be in the expansion? 5. It goes from 0 to 4. That's 5 different numbers. And then it's a to the power of n minus j, which is 4 minus j. And then b to the power of j. And that, when you expand it, will give us the whole expansion. So let's start setting it up. So j goes from 0 to 4, so it starts at 0. So 4 choose 0 initially. And then 3t squared, parentheses around it, to the power of 4. Because 4 minus 0 is 4. And then b gets raised to the power of 0. Plus. And keep going. Now j is 1. So 4 minus 1 is 3 for the first exponent, and then second exponent is just 1. And 4 minus 2 is 2 for the first exponent, and the second exponent is 2. Once we leave DC not room for work. 2 more terms. By the way, these exponents should all add up to what in this problem? 4, and so not only to pay attention to, just, I'll try to not make mistakes, but if we do make mistakes, we'll try to catch those mistakes. All right. Now, the numbers for 4 choose 0, 4 choose 1, 4 choose 2, once again, we're just going to look those up. Turn your paper over, look up Pascal's triangle. And what are the numbers we're going to use for this problem?
1, 4, 6, 4.
Yeah, that one, the line where n equals 4. And so, which there's 5 numbers there, by the way, and you should have 5 terms. So, I should check those things. So fill that in. 1, 4, 6, 4, 1. And then let's just go through it. 3 to the power of 4 is what? Good. So it's 81 t to the power of 8. Because when you raise to the power, the shortcut is to multiply exponents. And then the power of 0 is 1, so that's just 1. Right? And then here's 4 times 27 t to the power of what? And then negative square root of 2 times u. Plus, be careful, the u, of course, is not under the radical. If you want to put the u in front of the radical, just to make sure you can't mess up, that's not a bad idea, but all right, let's keep going. This is 9t to the power of 4, and then this is 2u squared. Yes? And then this is 3t squared. Listen, one little thing. Watch. We're about to do a radical cubed. Well, you need to be able to do this quickly. My point is, isn't this just going to be 2 radical 2? You should be able to do it that way and save yourself extra time, extra writing. And it will be, in fact, negative 2 radical 2. So this cubed is this, and then that. Or to put it another way, this 2 right here was this squared, right? So take that times another negative square root of 2, and that's where you get this one. All right, and then this one's 0. What's the last? What does this become? More than. First, it's positive 4 e to the power 4. This we agreed was 2. Well, then that means this is the same as that squared, which means it's 2 squared, which means it's 4. Now, I'm serious. If you want to raise something to the power 4, realize you can just square it and square it again, and a lot of times that's easier. Yes? To the power 3? That's this right here. All right, let's finally write a final answer. I think it's pretty good. Right there, I said, there's other ways to do it, but you really should be able to do this. Realize you multiply radical times itself 3 times. 2 of those times is going to give you a whole number. And that's it. Or, of course, it was a negative, so it was a negative answer. The other thing I said is, look right here. This 2 was this times itself twice, right? This squared. So you could just take this times a third factor to get this. This times another negative square root of 2 gives you this one here. So, all right. Once we're writing this out, that's the first term. What is 4 times 27? Second. So it would be minus 108. In here, once again, I'll leave it up to you. In other words, if you want to put the square root of 2 first, in fact, let's show it the way. A lot of times you want to put it after, just so it's unambiguous. You can put it before. Just make sure it's absolutely clear that the t to the power 6 and u come after. And then plus 54 times 2 is another 108. T to the power 4 u squared minus 12 times 2 is 24. That equal to t squared u cubed plus 4u to the power 4. Notice, by the way, in our final answer, the exponents didn't all add up to 4. But that's because you had t squared to the power, so it's going 8, 6, 4, 2, 0. Whereas the second exponent just goes normally 0, 1, 2, 3, 4. So it's a little different. Still, when you're setting up, the exponent should add up to 4. A little different. By the way, just for the record, if I took off that and that, then basically what we have is a way to raise any number that looks like that. It'd just be a number then. But 3 minus square root of 2 raised to a power could be computed using binomial theorem. Actually, we'll do that with the complex number shortly. Yes? Yeah. All right. This you have in your paper. And we just did this as part of the last problem. And frankly, on the problems that we've done so far, I don't always take the time to write this out. Probably isn't a bad idea, but it's all you're doing is setting it up. Here, let me write out the actual normal formula again, and then I'll write out the answer. Well, it's going to ask what that is. What it was, but it's that. So, what is n? So, j is going to go from 0 to 17. And right here, the 17, choose j. And then a is 3x, and then parentheses to the power of 17 minus j. And then b is negative 5y to the power of j. Everything gets replaced except for j because it's go here. So plugging in a and b. Okay? You try the next one now. Okay. And like I said, it's not a bad idea to just set that up around all these problems that we've done. I just write these things. Won't write them. All right. Back to Friday's note sheet. Find this problem from the back of Friday's note sheet. Sure, you had that out. I asked you what the Pascal's triangle is earlier. All right. This one's nice because, well, frankly, it's very small. Let's find one term. Okay. So look at this. I'm going to set up the binomial theorem. So J is going to go from 0 to 10. J, 3x to the power of, what goes here? 10 minus J. Negative 1 to the power of what? J. But we only want one term. Listen, first of all, how many terms are in the expansion of this? 11. We're not going to write out all of the terms. That'd be a waste of time. So you need to figure out what J is for the particular term we want. What is J going to be for the particular term we want? Not 7. All right. We want the exponent on x to be 7. The exponent is going to come from this. What would J have to be for this to work out to 7? I know you've never seen the problem before, but, you know. All right. Just stop. So J must be 3, which makes the exponent there 7 like we needed it to be. But that's the trick. Now listen to me. I know this is actually in your Pascal's triangle, but we're going to compute it. Because I should have made this numbers a little bigger, because the point is you're going to have an assessment on Wednesday, a non-calculator assessment, and some of the numbers, like this kind of problem, will make numbers too big to just look up. Anything beyond what you have in Pascal's triangle, you have to be able to compute. Here's your formula, by the way. Let me give it, you have it on your sheet, but write it down again. N choose J is computed by doing n factorial over J factorial times n minus J factorial. And it's on your sheet already, I think it was n choose R. But whether it's R or J, it's the same formula. So to compute n choose 3, 10 choose 3, it'll be 10 factorial over 3 factorial times 7 factorial. Because I think 10 minus 3 is 7. Now, right here, you want to cancel, and you want to cancel the biggest ones first. If I cancel the 7 factorial out of the 10 factorial, what's left? 8, 9, and 10. Let me watch. This is a big deal. This is how you need to think. Because there is no way you're computing 10 factorial. It is way too big, okay? So here, watch. 7 factorial means 1 times 2 times 3 times 4 times 5 times 6 times 7, right? 10 factorial means 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. So what are the common factors? 1, 2, 7. That means those go away. What's left? 8, 9, and 10. Okay? So if I ask you to do, let's say, 28 factorial over 25 factorial, what's left? 26, 27, 28. Or 28, 27, 26. After you cancel. Okay? So here. So after we cancel, we're left with 8, 9, 10. And then 3 factorial is 1 times 2 times 3. You don't really need to write the 1, but I would just write that out. Because then you can finish canceling. So 2 goes into 10 5 times, I'm pretty sure. 3 goes into 9 3 times. But I'm serious, I would show them the work exactly like this. And then multiply it out. 8 times 5 is 40, times 3 is 120. By the way, go look on Pascal's triangle and look up 10 choose 3. Which number you should be looking at? No, I know it's 120, but is it first, second, third, fourth, fifth? Which one is it? The fourth. J starts at 0, 0, 1, 2, 3. When you get to J equals 3, you're in the fourth term, yes? So, like I said, frankly, if this had appeared on the assessment, you could have just looked it up and it'd be fine. But I need you to practice calculating because you have to calculate some of them. So that's 120. 3 to the power 7 is 2187. Write that down. And then that's -1, of course. So, all right, calculate it. 2187 times 120. And I mean by hand. Crank it out. Three to the power 7. That's what I got. I feel like I messed up somewhere here, but you're right. By the way, there's something wrong with how I expressed my answer. Here's the problem. It asks for the coefficient. That would be this. And I'm serious. Some questions ask just for the coefficient, some ask for the whole term. If it asks for the whole term, you'd include the x to the power 7, right? The whole thing. Either, erase this or just circle the coefficient part like I did, and I'm good. But I'm going to check to see if you actually can read and know what the stuff's what problem's talking about. Okay? So if it asks for the coefficient, give me only the coefficient. Credit. All right. Look at the next one. Let's set this thing up. So, and once again on these, I would set up the Binomial Theorem. So it goes n choose j, a to the power of what? Good. And then -y to the power of j. So what do we want j to be this time? No. Yeah. It's actually the exact same problem except for that's the question slightly differently. I mean, isn't the only difference that instead of -1 it has -y? Yes? And then here, of course, it didn't ask for when would the exponent on x be 7, but rather it asked when would the exponent on y be 3, which is at the same time when j is 3. So we're really going to set it the same way and get the same answer. Here, let's just set it up. It'll be 10 choose 3 again. It'll be 3x to the power of 7 and -y to the power of 3. And I'm just going to write the answer we got last time because we already did all that arithmetic. Except for here, it would be x to the power 7, y to the power 3 term. And so, like I said, same answer, slightly different question. In the bookwork, it asks questions like, okay, what's the coefficient of the x to the power 7, y to the power 3 term? They didn't ask the way here, they just asked what's the coefficient of the y to the power 3 term. But so I'm saying, be careful, they can phrase it different ways. By the way, which term in the expansion would that have been? Right? Because j starts at 0, so when j is 3, you're at the 4th term. Which is how you need to think about the next problem. If you're at the 7th term, what is j? No. Listen, this is an easy thing that it's very easy to mess up. All right, look. Let me do this. J equals 0, j equals 1, j equals 2, j equals 3, ... This is in the 1st term. 2nd term, write this down. I'm serious. 3rd term, ... When you get to the 7th term, what will j be? No. 6. No, not 8. J is always 1 less than the term number, yes? On the 1st number, j is 1 less. J starts at 0. So 1st, 2nd, 3rd, j is 0, 1, 2. So when you get to the 7th term, j will not be 1 more. It never was 1 more. Okay? Listen. I'm going to highly recommend you write this out every time. Because I'm telling you, that is a mistake people make. They either use 7 or 8, not 6, and then of course it's all wrong. And so it's an easy relationship, but it's also easy to get backwards. You add one when you're supposed to subtract one, and then you've got it wrong. So here, let's set it up. Actually, we don't need this whole thing because we just want the one term. N is 8, so it's 8, choose 6, because we determined we're using 6. And then y to the power of what? 2. Isn't this n minus j? And then b, the power of, because j is that. Now, 8 choose 6. Go look it up. Tell me what you get. If j is 6, you're looking at the 7th number. You should be in the 8th row. Okay? Let's compute that. You need to practice. Like I said, on the assessment, if it's on the chart, you can just look it up. But there'll be ones where you have to compute them, so let's get the practice in. So 8 factorial over what times what? 2 factorial times, or actually 6 factorial times 2 factorial. Order actually doesn't matter, but it's n factorial over j factorial times n minus j factorial. All right, cancel first. Cancel the bigger out of there. What's left? Div? What factors are left when we cancel? 7 and, yeah. And then 2 factorial is really just 1 times 2, so I'm just going to put 2 there. I'm pretty sure that's a 4, and turns out you looked it up correctly. It is 28. So that's 28. That's 729. So now multiply out 729 to 28. And tell me what you get. Is that what other people got? And this time it did ask for the whole term, so make sure you give the whole term as your answer. Okay? All right, we're on the new note sheet again. And before we start this, let's talk about I to the power. There's a pattern to it. I've shown this before. I squared is negative 1. If you multiply that by another I, you get negative I. If you multiply that by another factor of I, look, you get negative I squared, but I squared is negative 1, so this is really the opposite of negative 1, which means it's 1. But that means if you multiply by I again, you get I, and it just repeats itself. And this is really I squared, which means negative 1, times I is negative I, and times I again is 1 again for the same reason. And it just repeats. And so here, what I want you to do is make a little baseball diamond and write down that pattern. It goes I to the power of 1 is I to the power of 2 is negative 1, I to the power of 3 is negative I, and I to the power of 4 is 1. Then I to the power of 5 over here, I to the power of 6, I to the power of 7, I to the power of 8, and so forth. Okay? All right, here, let's start subbing this up. We're going to do a full binomial expansion again. It's not variables now, it's a complex number that we're raising to a power. Let's see, 6 choose j, 5 to the power of 6 minus j, I to the power of j. And let's just start writing it out. So 6 choose 0, and 5 to the power of 6, I to the power of 0. I to the power of 5, I to the power of 1, plus 6 choose 2, 5 to the power of 6 minus 2, I to the power of 2. 3, plus I to the power of 3. What, 2 more terms? 2 more terms. for starters, I want you to go, and anyone's done writing, go look up our numbers from Pascal's triangle for us. There should be 7 numbers in that row, right? The row that goes 1, 6, 15, then what? And then, of course, it repeats, so 15, 6, 1. All right, for the powers of 5, I'm going to work backwards. It just seems easier to me. So 5 to the power of 0 is 1, 5 to the power of 1 is 5, 5 to the power of 2 is 25, 5 to the power of 3 is 125. You should know these. The next one is 625. But then they're a little bit beyond what you should have memorized. So find out that and tell me what you get. $25 times 5 is what I'm asking you to do. 125. And actually, multiply that by 5 is not bad, because 3,000 times 5 is 15,000. And 125 times 5 you already did to get to 625. So 15, 625. All right. Now we need to do the powers of I. So I to the power of 0 is 1. I to the power of 1 is I. I to the power of 2 was negative 1, right? I to the power of 3 was negative I. I to the power of 4 was what? 1. I to the power of 5, you're here, so it's I again. And I to the power of 6 is the same as I squared, so it's negative 1. All right. This first one is 15,625. That's easy. I need some of you to figure out 6 times 3125, and some of you to figure out 15 times 625. And the rest will be easy. So some of you calculate this, some of you calculate this. Seven, 1740. And this one is 2,500. And this one, 375. And then this one I think we can do. Now, we're not done, because there's no variable, so you actually have a bunch of terms you can combine. Before we do so, though, what patterns do you see? Yeah, I mean, you're right. Most of them are multiples of 5. That's true. Do you see that they go real, imaginary, real, imaginary, real, imaginary? Yes? Every other term is an imaginary term. And then as far as the signs go, look. If you look at our diamond, it goes positive, positive, negative, negative, right? And then it's going to be positive, positive, negative, negative, which is exactly what we see here. Positive, positive, negative, negative. And if we kept going, it would be positive, positive, negative, negative. There wasn't anything after that. But anyway, all right, listen. I need some of you to combine all the real numbers. So 15, 6, 25. Wait, yes? Well, then why didn't you say so? No, I'm coming there. Good. All right. Now, some of you can combine all the real numbers. There's 4 of them, right? And then some of you combine all the imaginary. but you still need to add this. All right. Subtract 1. Is that doing finish the real part? Second? Okay, good. And now, is it when finish combine the imaginary? 16,000? 16 what? Does anyone else get the same? Let's see. Yeah, it should be 80. Yeah, 50 and 30, it's 80. So listen, stop with the balloon. We just raised a complex number to a power, and it was a bit of a pain, but that's what you get. If it was a, all right, we can do this one more time. You know what? We already did one with radicals. I'll do practice on your own.